Okay, so now we zoom into these photosynthetic pigments. So we say that a photosynthetic pigment, when used the word pigment, basically means that they have the ability to absorb, okay, the light energy. Are you clear? Okay. So photosynthetic green plants, they have 6 closely related photosynthetic pigments, but in our syllabus only focus at the first 4, which are chlorophyll A, chlorophyll B, carotene, and xanthophyll. Okay, so this pigment, as I said, that we can actually divide them into two groups. One group is called as the primary pigments. The first group, okay, primary pigments. Not all can become primary pigments. Only 2 forms of chlorophyll A. Either they had a peak absorptions at 618 nanometer or 700 nanometer, like what I said just now. Okay, how about the rest? The rest will be called accessory pigment. Okay, accessory pigments. And what their role? Okay, we're going to look at this. So for example, chlorophyll A, chlorophyll B, carotenes, and that consists of carotenes and xanthophyll. They are accessory pigments. So it means that if I am chlorophyll B, no chance at all for me to become the reaction center at all. Like us, no chance to be a royal family at all. Okay, so means that no way. I mean, we fight for the reaction. I want to be a reaction center, useless. Okay, only chlorophyll A. Even you are chlorophyll A, not necessarily you will be the. Okay, you will be the reaction center, because you have to show that you are the peak. You have the peak absorbance at 700 or 680 nanometer. Okay, so they form a cluster, as I say that. So this pigment arranged in the light harvesting cluster known as photosystem. So we have several hundred accessory pigments surrounding one primary pigment. So energy of the light absorbed by the different pigment is passed to the primary pigment. So the primary pigment actually forms the reaction center. Okay, so we have learned about this. So if you want to study, okay, if you want to study the pigment, so now in terms of the plant, okay, we have this pigment. So this pigment actually we can separate them. Okay, we can separate them. How we separate them? We can separate them based on 2 types of methods. So it's the same type of method, but different way. We call it as a chromatography. So the mixture, chlorophyll A, chlorophyll B, xanthophyll, carotenoids, we can actually separate them. But how to separate them? We use a method known as chromatography. So we can use a paper chromatography, which have the cellulose, okay, or thin layer chromatography, which use silica gel. Okay, silica gels as the stationary phase. So what we're going to discuss now will be a little bit complicated, okay, in terms of the principle. Okay, so if any question, feel free to ask. So what is chromatography? Chromatography actually based on 2 principles here. One is the adsorptions. Okay, adsorptions. Another one is based on solubility. Okay, what is adsorption? Adsorption basically means interaction. Okay, basically interaction. Now, you try to imagine in this classroom. Okay, you try to imagine this classroom. So I try to walk past each table. Are you clear? So I am the pigment. Okay, I am the pigment when I walk past through. When I walk past through, if I have a very huge interaction with all of you, I talk to you, I talk to anyone, so I move slowly, turn off. If I have a very high adsorption, I tend to interact with the cellulose fiber, with the silica gel. When I pass to one, talk to you, pass to another one, talk to you, talk. So I move very slow. But if my adsorption is very, very low, I don't care, I just walk. Then what will happen? I will move fast. So different pigments, they have different adsorption. That means interactions with the silica gel or cellulose fiber. So in this case, you can write down adsorption high, move slower. Okay, adsorption low, move faster. Okay. So generally, it's something like go shopping. If today we are already focused, okay, I'm going to buy groceries. I should go to the grocery and then come back and finish. Okay, but if you say, okay, I buy grocery, but I still walk into the clothes shop, that means I go take and then go to the what we call this, gadget shop, definitely it take longer time because higher absorptions. Are you clear? Okay, that's one. Second, solubility. Now, how solubility actually happen here is the pigment, we have to dissolve them first. Okay, try to imagine if solubility is high, it tends to solubilize in the solvent. So solvent can carry them, go further. Clear now? Are you clear? You try to imagine that if you have the cup of the highly solubilized sucrose, they're always soluble. But if let's say they are partially soluble, they tend to precipitate out. Can I see that? Like Milo. It's not soluble. Can I see that? Are you clear? They tend to precipitate out or sink down. So it means that when the solvent carry the pigments, if the pigments solubilize well, it will follow the solvent and move. So higher solubility move further. Clear now? They follow the solvent. But if let's say they are not solubilized, they don't like to be solubilized, so they precipitate out. So when they precipitate out means that you don't want to move further. So based on the interplay between these two factors, we will be able to segregate out the pigments because different pigments, they have different solubility and also different absorption. Are you clear? Can? So how we perform this? Look at this diagram. How we perform this? So basically, this blue color is the solvent. Solvent also known as a mobile phase. So it's mobile movement, mobile phase. Because solvent are going to travel up this strip. This strip is known as the paper chromatography, paper or thin layer chromatography. Are you clear? So it depends what kind of material. If let's say the material is the silica gel, then we call it as a thin layer chromatography strip. But if let's say it's a paper, it's a cellulose paper, so we call paper chromatography. Okay, strip. So it doesn't matter as long as you allow the solvent to move out. So when solvent move out, can you see that? When solvent move out, it will carry the pigments and then together. As I said that when the pigments move, when the pigment move, what they do? They do have this property, absorptions and solubility. Can you see that? So I tend to carry, I'm solvent, I tend to carry. Okay, I mean the pigments to move. But this pigment always want to interact with the silica gel, don't want to move. I don't care, I leave them behind. Can you see that? So high absorption. Okay, or those that tends to follow me and walk, then I will move, I will bring them, move further. So that's why we will be able to actually separate the pigments based on their solubility and also the absorption. So generally, okay, write down generally. So if this is my TLC, thin layer chromatography, the pigment's high, this is pigment low. Generally, this one absorption is low. Okay, absorption low, solubility high. Then it tends to move further generally. Are you clear? So those that cannot move further, the absorptions confirmed, okay, will be high, solubility is low. So based on these two ratios, the interplay between these two principles, we will be able to segregate out the pigment. Are you clear? Okay. Once we have separated the pigments, then we focus at one of the pigment that I want to study. For example, I want to identify who is this pigment. Okay, if I want to identify who is this pigment, then we have to calculate the value called RF value, retardation factor. Okay, so this is my strip. This is my strip. So the strip here, we put in the pigment initially. So let the solvent carry this pigment up. So at the end, separated the pigment 1, pigment 2, pigment 3, for example. Are you clear? And solvent will continue to move, right? Solvent care, you want to stay, you stay lah. Solvent continue to move. So at the end of the process, we do have this called solvent front. Solvent front. Okay, the solvent continue to move, right? So in this diagram, can you see that? This is the solvent front. Okay. This one we call origin. And we study the pigment. Let's say this pigment I want to study. So what we can do, we can measure the distance traveled by the pigment. And we do have the distance traveled by the solvent front. So we calculate the RF value. So the RF value is equal to the distance traveled by the pigment divided by the distance traveled by solvent front. Are you clear? Okay. So from RF value, then we can go to the database. When you go to the database, you will be able to actually figure out who is the pigment. Okay, I want to know who is the pigment. Okay. So now, example here, I have this pigment A, pigment B, C, and D. Given that the distance traveled by the solvent front is 95.5 millimeter, okay, RF value given from a database. So now you have the pigment A, B, C, and D. Distance traveled by the pigments in millimeter, 90.5, and so on. So calculate the RF value and identifies the pigments from the database. Please do it now. Okay, so now we have done for the separations already. So we have done the separations. Now, what we did just now, the separation, okay, is useless. We just can't identify. But if you change the chromatography to another way of chromatography known as column chromatography. Now, what's mean column chromatography? Column chromatography basically means that, to try to imagine, we pack silica gel not on the paper, but inside your burette. Can you imagine? I pack a silica gel inside the burette. Then I pour the pigment. When I pour the pigment, it's something similar to the paper chromatography, can or not? The pigment start to move. So high absorption, stay, move slower. Low absorption, move faster. So burette, we have the tab, right? We can open and close, right? So we have the beaker at the bottom, we open. We open the tab, we let the first pigment drop. But done of the tab. Take the second beaker and then on. Then let the second pigment pass through the burette and then you collect. So column chromatography allows us to collect the pigment and separate the pigment. But paper chromatography and TLC, thin layer chromatography, cannot. They just show us, oh, got 5 pigments, that's all, to stop. I'll identify who is the pigment, that's all. Can I actually separate them? I separate them, but I cannot purify them. I cannot purify, oh, chlorophyll A, chlorophyll B, and xanthophyll. But by using the column chromatography, you write, open. No, finish. Not the second finish. Because it got color. We can do this. But if a solvent no color, then cannot lah. How do you know that which one drop? Are you clear? Because pigment, they have different color. Oh, green color, and then orange color, yellow color, for example. We can actually separate them. The longer the burette, the better the resolution. Are you clear? Okay. So what we're going to do here is, once we separate and collect them already, we can actually use this system known as the calorimeter, something like calorimeter here. Not colorimeter, sorry. Okay, color. Okay, so this calorimeter known as spectral photometer. Spectral photometer. Still remember we talked about this in your enzyme notes there. We have the spectrometer and also the photometer, right? Okay, spectral. So first we generate different wavelength. We have the light with different wavelength. For example, we started with 400. And then we let this 400 nanometer light pass through the chlorophyll solution. Can I see that? Pass through. So then we detect how much the absorbance. And then I change from green light to different color light. Okay, so you plot a graph. So this graph is named as absorption spectrum. Okay, absorption AB, not AD. Yeah, absorb how much light they absorb. So in this case, can you see that green color? Any absorption? Almost 100. Very, very few absorption. There's also why the plant look green, because of the chlorophyll. So don't be thinking, oh, plant green color, so that's why I shine the green color light. They like green color. They don't like green color. That's why they reflect green color. So now if you think back, if you like red color shirt, basically you don't like red because you reflect all the red. Correct enough? Physics. You get the idea? So the plant, the leaf is green color because they reflect green color. They don't like green. What they absorb? They absorb blue and red. Can I see that? So this, we generate a graph. So this graph is termed as the absorption spectrum. Can you see that chlorophyll A absorb the blue and the red? Can you see that? Okay. So what we're going to look at here is how we do this. Okay. So the ability of the pigment to absorb various wavelengths of the light can be measured with instruments known as the spectral photometer. Spectral photometer. Okay. So basically, we do need to generate different wavelengths, allow the light to pass through the solutions, and then we detect how much transmitted. Then we can calculate the absorption. So it's transmitted almost 100%. What is absorption? 1 to 2%. So we change. So we start at 400, 410, 420, 430, and so on. We plot the graph. Are you clear? So once you plot a graph, you have this graph called absorption spectrum. So what is the principle of spectrophotometer? So you can read it by yourself. So basically, we need to separate the color of the light into different color or different wavelength by prism. So one by one, the different color of light pass through the sample. Okay, then you can transmit through the photoelectric tube, which convert the light energy to electrics. Then you'll be able to know how much light has been absorbed. So if let's say transmitted 70, I check 70, so absorbed 30%. If I check 100% transmitted, so means that 0% absorbed. So you calculate, then you can plot the graph. So this graph is known as the absorption spectrum. Are you clear? Okay. Now we do have another spectrum known as the action spectrum. Action spectrum basically means that I want to look at the overall reaction of photosynthesis. Which wavelength is the best? Are you clear? So in this case, do I collect the chlorophyll? No, I collect the plant. I ask the plant to carry out photosynthesis, and then we check which one gives us the best photosynthesis, which wavelength. Are you clear? So it means that in this diagram, 9.9. So I plot the graph, different wavelength and the rate of photosynthesis. For example, we refer to how much O2 release per unit time. Are you clear? So this is action spectrum. Why call action? Because it gives us the actions of the photosynthesis. Can you see that? That's why I call it action spectrum. Okay, this one, the first one, how much they absorb the light. Cannot. We use a pigment. How much pigment absorb the light? So this one is the absorption spectrum. And if you look at the absorption spectrum and action spectrum, if I ask you to compare, what you can see? I ask you to compare here, what you can see? In terms of the shape, are they relatively the same? They match, right? So why they match? Why they match? You can see that higher absorption at this between 400 to 500. Higher rate of photosynthesis. So indicates that the light energy absorbed by the pigments is used for the photosynthesis. Can you see that? Another region is between 650 to 700. Can you see that? Are you clear? But one part I'm not really okay here is between 500 to 600 because it's near to zero absorption. You realize that the absorption is near to zero, but photosynthesis is still high. It's not near to zero. Why? So we have to know the accessory pigment, what we learned in our syllabus, only chlorophyll A, different form chlorophyll A, chlorophyll B, xanthophyll, and carotene. Can I see that? But the plant won't have these four only. We still have many, many types of the photosynthetic pigment, which is minority that we did study here. They're in charge for this part of wavelength. So that's why because in our study, only study carotenoids, A and B. But how about other? You'll find it. Can I see that? Different types of the pigments. So they do help to absorb the light, but they're minority. We don't study them. But doesn't mean that they are not there. Are you clear? So they are there to absorb the light and light intensity, light energy, pass on this light energy, or pass on the energy to the reaction center. So therefore, in the action spectrum, we can see that there is, okay, reactions. So both chlorophyll A and B have absorption peak at the blue and red, okay, spectra. So the carotenoid also have two peaks at the blue spectra. So the action spectrum actually peak in the blue and red spectra. So this result indicates that the absorbed light energy is used for the photosynthesis. Okay. Those who are online can help to screenshot the answer and put it into the group. More, it's clearer, right? So by comparing these two figures, the action spectrum for the photosynthesis is much broader than the action absorption spectrum of the chlorophyll A. Partly because accessory pigments will be different absorption spectra is there, okay, including chlorophyll B and carotenoids that broadens, okay, the spectrum of color. Are you clear? If you depend only on the reaction center, it's much more narrower. But this one broader, why? Because we have different form of chlorophyll A. Are you clear? Okay. So both chlorophyll A and B absorb a slightly different wavelength in the red and blue part of the spectrum, but generally they absorb blue and red. Reflects green. So they don't like green. Don't try to bring color to them. Useless. Okay? So between 500 nanometer to 600 nanometer wavelength, the absorption spectrum show the light absorption is near to zero. However, the action spectrum show that the rate of photosynthesis is higher than zero. Much more higher than zero. So this is because of the other accessory pigments. Not chlorophyll A, chlorophyll B, carotenoids, but other kinds of the pigments that absorb the light energy, pass on this energy to the reaction center. Okay, so therefore the action spectrum here show the the rate of photosynthesis. So with this, I have done for today. So off the record.